All right, how's everything going? So, a fair bit of confusion on
Oh, you did?
Knapsack Problem,
did
dynamic
for-
programming, algorithms. So let's go through some details of this based on questions I'm getting. First is this business of finding the maximum value inside this loop. So you've got some arrays which tell you the weight and the value of your items, and you've got something that tells you how many items you have, so how big these arrays are. And your goal is to find max val of some capacity. And so the algorithm was to imagine one by one putting each one of these items in your bag. That gives you some value and it takes away some capacity, and you recursively call max val to find out what the best is you can do, assuming that you've made that move. And so you have a series of calls like value of item I plus max val of capacity minus the weight of item I. And that's the essential calculation you're going to do. You're just going to put it inside a loop and you're going to do things with the results. But basically you're going to call this for all values of I, right? So for I from 0 to number of items minus 1. And what do we do with this? We want to do this over all values of I and find the largest result, right? So the first thing is we can't do this if the weight of item I is bigger than the capacity. Okay, if it's equal to the capacity, that's fine. If our phone weighs 2 pounds and our bag holds 2 pounds, we can put the phone in the bag. If the phone weighs 3 pounds and the bag only holds 2 pounds, we can't put it in. So if weight I is bigger than capacity, then we just want to go back up to the top of the loop. You can do this multiple ways. You can say if the weight is less than or equal to the capacity, do this stuff. You can say if the weight is bigger than the capacity, continue, which brings you back to the top of your for loop, whatever your style is. So assuming that it's a legal weight, we want to calculate this value and we want to find the largest of all of these values, right? So what do you do with a running sum? You initialize a sum to 0, and then at each point when you have the thing you want to add to it, you add that to your sum variable. How do you do a running max? You initialize your max to 0, and then each time you have something that might be a new max, you compare it to your current max. And if it's bigger, then you update your current max. So we can do some initialization like best equals 0. And then you can say if this thing is bigger than best, well, let's do this. So do your calculation, save that in some temporary variable, and then it's just if temp is bigger than best, then save that. And when you're done with all of this, return best. Does that make sense? So that's just a running calculation of a maximum value. You're safe initializing it to 0 because if it turns out nothing fits in your bag, a max val of 0 is the right thing to return. Right? We can't get any value out of this bag, so that's a safe initialization in this case. And it'll only change when this turns out to be something bigger, and you could just throw an if the weight of I is less than or equal to the capacity, then if this thing is bigger than best, set best equal to that. Okay, so that gets you your best value. If you're keeping track of inventory, if you're keeping track of how you get that max value out, you need to know not just what the maximum value is, right, this return integer value, but you need to know what combination of items gets you that maximum value. So when you find a new best, you need to save not just the maximum value, but what item number gave you that best value. So that when you come out of your for loop, adding item, best item, so that you know that's what gave you the best result. But you also need to know what the inventory of items was here that gave you this max value. So you're going to want to save that also. So, you've got various parts and pieces here. So I would suggest something like this. Right, a result that will store a value and an item count. So we can return that from max val, and then maybe try this. Let's see, do we need that? I don't know if we need that. I don't think we need it. I think you just want to take a capacity and return two things now. The value, that's the best you can do, and the inventory of items that gets you that best result. So inside here, you need to save this return value, or when you come out of here, you know that item I gives you the maximum value, right? So so for each of your items, alright, call max val, save your result if result value is bigger than best value. Alright, save your best value so you know what the new max is, and do something like best result equals result. So when you come out of this for loop, best result has the maximum value and it has the inventory that gets you that best result. So can say best index equals I. Okay, so what's your setup when you exit? Best result dot value is the maximum value. Best result dot item count shows how we got whatever the max value was that we had inside our calculation. And best index is the item number that we were using to get that. So if you want to know how you get this best result, here it's the items that you use to get the max value out of that diminished capacity bag with one more item, which item, whatever your best index item is, right? If I was equal to 3 and that's when you got your final maximum value, it means your best solution for this original capacity is the best solution for this diminished capacity plus one more of item 3. So save that item number, that's what I'm calling best index, and then just bump up the count of that item in this item count array. Does that make any sense? This is like really easy to see and really hard to like convey. So here's an item number, here's a weight, here's a value. All right, hypothetical example, and these numbers are not going to be correct. So let's say we want to find the maximum value we can get out of a bag that holds 10 pounds. Okay, we're not going to go into the recursive calls, but what does this look like? There's three possibilities. If we start with item 0, right, item 0, we have a value of 10 plus max val of 10 minus 2. If we start with item 1, we get $22 by using that item in our bag, and then we lose 4 pounds of capacity. So we call max val of 10 minus 4. Item 2, we get $30 from putting that in our bag. Bless you. We diminish our capacity by 5 pounds, so we have to find max val of 10 minus 5. Okay, totally fictitious numbers, right? Suppose that this turns out to be equal to 17, and this turns out to be 42, and this turns out to be 39. Okay, what do we know? We know that our final max value for a capacity of 10 is going to be 42. So we want to return 42. But what can we say about the inventory of items that get us that? Whatever the inventory of items is that gave us max val of 6, if we add one more of item 1, that's the inventory that gives us max val of 10. Okay, that's the whole idea. So maybe max val of 8. The way that we got that inventory was item 0 we had 1, item 1 we had none, and item 2 we had 3. Alright, so that's how we got our $17. And maybe this max val of 6, the way we got our $42 was we had item 0, we had 1, item 1 we had 10, and item 2 we had none. And max val of 3 was, something similar. Okay, well, since this is how we got the max val of 6, and our max val of 10 is what we get, what we do to get max val 6 plus one more of item 1, the final inventory here would be right? The inventory we used here, plus one more of item 1, so 11 item 1s, 1 item 0, no item 2s. So think about that and try to code it up. Like I say, do this last, but some people are at this point, they've got the max val working, so they're down to figuring out the inventory. So this is the idea there. How you code that up? Do you have a composite structure? Do you have parallel arrays details? Right, that's up to you. But there's an idea for how to sort of track the inventory. Other questions? All right. So let's talk a little more about tree balancing. So let's talk about red-black trees. So red-black trees are not AVL trees. They're binary search trees, but they don't have perfect balance. Okay, an AVL tree is always balanced in that sense of the heights are within 1, the left and right subtrees are balanced. All the balance factors have absolute value less than 2. Red-black trees do not have these properties. They can look really, really unbalanced, really lopsided. But they're balanced in a different sense, okay, which we're going to look at. We're not going to go into the details of how we manipulate red-black trees because it makes AVL trees look like child's play. To me, at least, red-black trees are really, right? But I want to just sort of give you the idea behind a red-black tree, just because it's a different approach to this idea of balance. And nobody knows really why they're called red-black trees. One story is the people who worked this out, they had a red marker and a black marker, and that's what they used. I think that's the most convincing story for me, so we'll run with it. Okay, so this is a binary search tree, and it has the following characteristics. So each node is either red or black. Okay, so you need a bit that tells you what the color of the node is. The root of the tree is always black. Leaves, which are always nil, are black. So we draw these trees a little differently. If you have a tree like 10, 5, 20, we imagine that there's these extra nodes off of here called nil. It's our null pointer basically, but we consider those to be nodes. And we do that because we want nil leaves to be black, so we just color these black. Okay, now it gets a little weirder. So if a node is red, both children are black. And by having these nil nodes, right, every node has 2 children. So even if your tree looks like this, right, this would be nil. So this 10 actually has 2 children, so we don't have to deal with leaves that only have 1 child. So if a node is red, both its children have to be black. If a node is black, its children could be red or black. Okay, but red nodes, black children. Okay, so here's the cool part. So the number of black nodes from the root to a given node n is called n's black depth. So if you start at the root and you move down to a given node n, and you count the number of black nodes along the way, that's called the black depth of n. Okay, it's the number of black nodes from the root to the given node. So here's property 5. All nodes have the same black depth. And we can call that the black height of the tree. So normally the height of a tree is the depth of the deepest node. Since all nodes have the same black depth, the height is just whatever that depth is. So let's make some picture examples. So root's got to be black. Can you actually see like the difference between black and red? Not very easily. That's a little better. Well, okay, we'll just label them. Alright, so there's black, black, black. Alright, that's a perfectly fine red-black tree. So the black height of the tree looks like it's 3. Right, 3 black nodes to every node. So that's fine. That's also fine. And that's also a fine red-black tree. Yeah?
So a node with 2 black nodes doesn't automatically have to be written?
No. Black node can have black children, red children, could be one of each. Like here. The only requirement on the colors is if you're red, your children have to be black. I should modify this. This should be all leaf nodes. Have the same black depth. Because obviously the root has a black depth of 1. So, but if you go down to a leaf, right? So here's leaf node, black depth is 2, black depth is 2, black depth is 2. One red node, both its children are black. Nils are black, root is black. That's a good red-black tree. Well, things can start to look a little crazy. So there's a root. How did I do? 1, 2, 3, 4, 1, 2, 3, 4. Red nodes have black children. Black height of the tree looks like 4. All the leaf nodes have a black depth of 4. This is a red-black tree. But there's more stuff over here than there is over there, right? So it's not balanced in the classic sense. But how unbalanced can it get? Right, it's unbalanced because the path from the root to one of these nodes is much shorter than the path from here to, say, one of these nodes. Right, so in the classic sense, since the height is within 1, those path lengths differ by at most 1. How much can the path lengths differ in a red-black tree from the root to a leaf node?
It depends on the shortest level and the remaining number of nodes on that level.
Okay. Can we quantify that further?
It can never be more than twice the height.
Yeah. So there's a factor of 2 in here. So suppose your shortest path has n black nodes. Well, your longest also is going to have n black nodes, right? Because that's got to be constant. And we might have some red nodes scattered in here and there, right? So our shortest path that contains n black nodes, how many red nodes can it contain? If we want it to be as short as possible. 0. Right? If it's got to have n black nodes, but we want this path as short as possible, don't put in any red nodes. So our shortest path is just n black nodes, one after another, after another, after another. If we want to lengthen it, we can start inserting red nodes somewhere. Well, we know the root is black. And we've got n of these. So where can we insert a red node? Well, we can't change the root, so it can't come before the root. Can we put a red node right after the root? Yeah, nothing wrong with that. Can we put another red node after that? Right, because red nodes have to have black children. So we got to take one of the black nodes and use that as a descendant. But after that, we could insert a red node. And then the next node has to be black, and so on. And so it turns out we can insert n red nodes. And so the longest path is twice the shortest path, worst case. In general, probably better. So the heights aren't within 1, but they're within a factor of 2x. And that's the main characteristic of a red-black tree. And 2x is not all that bad. It's balanced enough that we can still preserve our nice log n and n log n characteristics. So when you want to implement a red-black tree, you have to look at what happens when you insert a node. And you insert a node, and I believe you insert red nodes because you're putting them down at the leaf, or black nodes because you're putting them down at the leaf, and then that affects the red length of a path, potentially. And so you need to recolor some things, and when you recolor something from black to red, you may violate the requirement that its children are black. And so you start getting into all these special cases, basically, for what you do to readjust the tree. And a lot of the readjustments is just recoloring nodes. But some of them actually involve things like rotations. And some of them involve looking at your parents, your grandparents, and your uncles. So a sibling at another level up. And so, like I say, it's just more complex than AVL rebalancing. But there's a set of steps you do, and you check for these conditions, and you apply the adjustments, and you're back to a red-black tree. What I think is interesting about red-black trees is that you have these properties right, which don't directly tell you, it's not a property that the path length has to be within blah, 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 right? But a side effect of the properties, particularly the red nodes have black children, gets you this degree of balance. So it's an example of invariance, things that we require to be true on the tree after we make modifications to them. All right, so that's all I'm going to talk about for red-black trees. There's more we could do with implementation. And there's other kinds of balanced trees. There's B trees, and there's 3 trees and 4 trees and things like that. And we're not going to go into that. And in practice, you don't spend your day writing tree balancing algorithms, right? You get a package that already does that for you. In Java, we'll use a bunch of classes that are already written for us to implement things efficiently, but it's good to know what's going on under the hood at some detail. All right, any questions or comments on that? So back to dynamic programming. Let me give you a second problem, which is kind of like a knapsack problem, and the solution looks very much the same. This is rod cutting. And here's the idea. You have a length of material, and you can sell this. Let's say this is 10 inches long. You can sell this for a certain amount of material. So a 10-inch rod, maybe you can sell that for 45 cents. But it turns out that most people don't want a 10-inch rod. Maybe there's a really, really common application for 5-inch pieces of this material. And if you sell a 5-inch rod, maybe that's actually worth 30 cents. Right now, if you sell someone the uncut material, it's cheaper because to get 2 5-inch rods that are cut is going to cost you 60 cents. You could pay 45, get the 10-inch and cut it yourself, right? But people don't have the tools for that. So you can get a premium for selling it at a different length. And so you have a table of and let me just order this, a table of how much you can get for different lengths of this material. So a 9-inch rod might be worth, only 40 cents. 8-inch might be worth more than 10-inch. And nobody wants 7 inches, and really nobody wants 6 inches, and whatever. And a 0-inch rod is worth 0. Here's my bag of 0-inch rods, how much you pay for it. And so the question is, how should you cut this rod up and sell it in order to maximize your income? Right? So simplifying assumptions, you don't lose any material when you cut it. Okay, so it's a perfect cut. Doesn't cost you anything to cut it, so that doesn't come out of your profit. You're just breaking it up into little sub pieces and selling those off, and there's always somebody willing to buy as much of the stuff as you have. So infinite demand. And so should I just sell a 10-inch piece? Should I sell a 9-inch piece and a 1-inch piece? Should I sell 2 5s? What's the way to cut this bar up in order to maximize the amount of money I get for it? And it's computationally complex to do exhaustively. Right, because I could cut it into one piece 10 times. I could cut it into one piece, 1 inch, 2 inch, and 7, 1, 3, and 6. We're getting back to triangles. And I disagree with that answer, by the way.
I don't know how they got it. I still don't.
Okay.
They don't have it written. They just
I looked it up, and there's only 2 integer triangles with
I looked
perimeter
at it.
10, and they both have repeats. So So if you don't get credit for it, we can fight it. So you want to chop this into some set of lengths, right? And this is like the knapsack problem, basically. It's a question of finding the best solution to sub-problems and then using that to find the best solution to your original problem. So again, max val of 10, and it's the largest of, well, if we cut off a 1-inch piece, we get a value of 1, and we have 9 inches left, so whatever we can do to maximize selling off that 9-inch piece, if we add one more dollar, that's our maximum value, assuming that we have a 1-inch piece in our solution. Or we could have a 2-inch piece plus max val 8, or a 3-inch piece plus max val 7, and so on. Or a 9-inch piece plus max val 1, or a 10-inch piece plus max val 0. And it's got the exact same structure as knapsack. It's this solution that involves finding solutions to smaller problems and then combining those. So anytime you have this repeated subcase example, subcase situation, you can throw dynamic programming at it and probably make it run efficiently. And this will turn out to be extremely efficient, because if we want max val of 10, we need to find max val of 9, 8, 7, and so on. But as soon as we have max val 0, that gives us max val 1. Right? And all of these will be saved in our result array. And so when we come down here and we want these other cases, we've already got these calculated. So we only have to do 10 recursive calls or so, and the others we just pull the answers out. There's another way we can do this, though, which is to work the problem backwards. So let's say step 0, find max val of 0. Well, we know that's 0. If you don't have any material, it's not worth anything. Okay, what's max val of 1? And let's just stick with this kind of goofy pricing table. And I don't know if it's an interesting table or not. So what's the max val we can get out of a piece of material 1 inch? It's just 1, right? There's no other option. All right, so if we have 2 inches, we got the following possibilities. We have we can cut off 1 inch and then find the max val of the remaining inch. We can cut off 0 inches and find the max val of 2 inches. And that's really it. Well, we already know max val of 1 is equal to 1. Sorry, that's 2 inches plus max val of 0. However, we know max val of 1 is 1, so this is equal to 2. This is 2 plus max val of 0, which is 2. So the largest of that is just 2, so max val of 2 is 2. So if we start with the case of 0 and we work our way up, right, we don't have to do any recursion. We've got these values stored, so let's do one more, max val of 3. So it's the largest of the following. Cut off a 1 inch piece, we get a value of 1, and then we have 2 inches left. Cut off a 2 inch piece, which gives us a value of 2 and leaves us 1 inch. Or cut off a 3 inch piece, which gives us a value of 15 and leaves us 0. And we've got max val 0, 1, and 2 already. So this is 1 plus 2 is 3. This is 2 plus 1 is 3. This is 15 plus 0 is 15. So max val of 3 is 15. And so we can work our way up like that to whatever value we want, 10 in this case. right? And in each case, we're not actually doing any recursive calls because we've already calculated all of the lower rod length answers. So you can do that with these problems. It's kind of a different feel. It takes a different type of coding compared to the recursive one, but it's effectively the same process. Although you may do more work like this. With the knapsack problem, we don't necessarily have to calculate the capacity, the max valve for capacity of, say, 7, right? Depending on the weight of your items. So here, we've got all the integer lengths, corresponding values, so we're going to end up calculating max valve for each of those. But with the knapsack, the way that your item weights are set up, you may not have to calculate certain values. So you might do more work like this, but it's in some sense more direct. So that's a rod cutting problem, and it's just another dynamic programming example.
So the math value is cannot take the negative.
Definitely can't do negative lengths, and we're assuming that you can only cut in whatever lengths are in the table, in this case just integers. But you could do it where, you know, there's no value in a 5-inch piece, for example, or something like that. And this is basically your inventory file, right? So it's just the pricing table. All right, does this make sense? Can you do this on a final exam?
Yeah.
If I give you a pricing table and ask you to find the max value?
Give me a week and a half.
I'll give you a week and a half.
Plus extra credit, right?
Do it.
Plus extra credit.
Plus extra credit. Extra credit if you actually bring in a rod and a hacksaw and find someone to buy it.
Done. Extra credit for everybody. We have a business plan now.
All right. Well, we got 5 minutes. Let me start a different kind of dynamic programming example. So this is egg dropping. Anybody ever do an egg drop contest?
Yeah.
Cool. We used to do one where I did my undergrad every year. They go to the top of the building and build a contraption to like try to protect your egg when it falls. They use the drop tower for that sometimes. Eggs or other things. So the idea of the egg dropping problem is you have a building with a certain number of floors and you have a certain supply of eggs. And your goal is to figure out what's the highest floor you can drop an egg from without it dropping, without it cracking. Right? So there's a cutoff somewhere. And there's all kinds of sort of obvious assumptions. So all of these eggs are identical to each other. Okay. If dropping from a given floor will crack the egg, dropping from a higher floor will also crack it. If dropping from a given floor does not crack the egg, dropping from a lower floor also will not crack it. So it's all kind of nice and deterministic. These eggs are also reusable. They don't get damaged unless they get cracked. So if dropping from this floor does not crack the egg, I can drop from that floor 100 times with the same egg and it still won't crack. And it doesn't change the way it will behave at other floors. So they're like idealized eggs. So here's the question. If you have F floors and you have E eggs, how do you figure out where that critical floor is? And the real question is, how many experiments do you have to run to answer that question? What's the critical floor? And we're looking for a guarantee that you can make to somebody. Because you might get lucky. You might take the egg and just go up to floor 17, drop it, it survives, go up to 18, drop it, it cracks, and that's it. 2 experiments, you got the answer. But we're looking for a guarantee. Okay, with F floors and E eggs, you're going to tell somebody, okay, it will take me no more than 5 experiments to answer your question. So we're trying to find that number 5. What's the guaranteed number that will suffice for you to figure out where the critical floor is?
Log F.
No, it's way harder than a log, but there's probably logs in there. And it should be an integer, right? And we got kind of 2 n's here, because it depends on the number of floors and the number of eggs. So if you have only 1 floor, it only takes you 1 experiment. And you really only need 1 egg. So if you have 100 eggs in 1 floor, it still takes you 1 experiment. If you have only 1 egg, how would you figure out what the critical floor is?
You have to start at the bottom.
Go up.
You got to start at the bottom and go up, because if you start on the 2nd floor and drop it and it cracks, you don't know if it would have cracked from the 1st floor, and you're out of eggs now. So if you only have 1 egg, the best you can do is say, okay, I'm going to need to run F experiments. I'm going to need to drop it from every floor, and if it survives all of them, then I know my answer. If it cracks at some point, I know my answer. So there's a few base cases here, right? If you have 1 floor, if you have only 1 egg, and then we want to figure out the general case. So think about that, and we'll talk about it tomorrow.